All right, let's go ahead and move through a couple potential electric potential problems for charge distributions. These are going to feel fairly familiar as far as the general path we take. I want you to be paying attention to the fact, though, that we are not solving for E. We're solving for potential, which is a really different quantity. I know it's related to E, but really stay in touch with the fact that it's a very different quantity and it's scalar too. But let's go ahead and get started by setting up our coordinate system and moving from there. For this problem, there are different coordinate system choices you can make, but the choice I'm going to go ahead and make is using the end of the rod as my origin. So I'll just define this spot right here as my x equals 0, and then I'm going to define positive x off in this direction here. X is how I'm going to need to move along, so I care most about where that is. So I can say that 2D origin is going to just be right here. I can call that. And just to be super clear about what I'm doing here, I can say that I've got my positive y or positive j hat upward, and then positive x or positive I hat rightward. Potential is not a vector quantity. So we probably, we don't hit this stuff quite as hard as we normally would with electric field, but it's still really important because we are moving around in a coordinate system. So we do need signs, right? We need an origin and we need signs, or we don't know where we are in that coordinate system. So then, just like with DE, with our electric field stuff, we have to define a differential element, dq. So I'll go ahead and do that. I'll define some little differential element that I'll call dq. That element also, of course, has some length that I'm going to call dx. And by now, you know the motivation for defining that, because we have to have some way of making our way through the charged material as we are summing it all in our integral to figure out the overall potential at point P. So if we were working electric field here, I would have you draw your DE in, of course, and this is scalar. There's nothing to draw, right? So it's nice that it's scalar because it's mathematically a little easier, but actually, I think conceptually it's a little bit harder because it's harder to wrap your mind around this quantity, the quantity of electric potential. It's not quite as clear cut as electric field. So remember that how I'm wanting you to conceive of this is electric potential as related to elevation. So a way to see this in your mind, many of us that do science are pretty visual. We like to have a picture of what we're doing in our minds. So the picture I'd like you to have is of elevation. So this is a positively charged rod. If this view was a top-down view, we would be looking down on, say, a ridge line. So this is high. The highest elevation is at the rod, and then the elevation would decrease as we move away from the rod, and that would happen in all directions. And everywhere until you get to infinity, your elevation would be above zero due to this positively charged rod. Okay, so enough about that. Now let's just go on and finish defining the stuff we need to define. So we know that we're going to have to define DQ, and we know that we're going to have to define R. Same moves we make when we're doing E, right? So let's look at what we have here. I have my x equals 0 on the left side of the rod. So that means that this quantity right here is x. And I know that my quantity R is always the distance between my differential element and my point of interest. So I know this is R. That's how R is defined. I'm told in this problem that the rod has some length L, so I'll go ahead and pop that in. And then by looking at this picture, it can help my brain see how these quantities relate to each other. A common mistake that students make is misdefining R, defining R incorrectly. And I think what that's coming from is a student not actually understanding physically what R is or where R is. And that to me is actually the larger problem. So if you draw it in your diagram and your written work, I mean, number one, that helps your brain understand what you're doing. It also shows, if I'm grading your work, it shows me that you know, that you understand physically where R is. And then it will help you to define R more accurately. So one of the things we need to do here is define dq. So let's go ahead and start doing that. So I'll have dq here, lambda dx. No surprise there. For this, in the same way and for the same reason that we did for our integration to find electric field due to a distribution. Our next move here is to define R. So have a look at the diagram, and we can see there if we're defining R is going to be quantity A plus L minus X. And if you define your origin in a different point, your R is going to be different and your integration bounds will be different as well, right? All that stuff has to be consistent and it all has to work together. When I grade these integrals, one of the first things that I look at is, do the coordinate system, the definition of R, and the bounds of integration all make sense together? Do any of those contradict each other? Do they all work together? And if those don't work together, then that's a sign to me that sometimes the students kind of making it up as they go along and maybe just like kind of writing in some memorized stuff, but there's no real understanding of what's happening in the problem. So that to me is pretty big red flag. So if you're not understanding that stuff, it's time to, we've had a couple weeks now, we've been into these integrals. It's time to start understanding what you're trying to express with the integral. So our equation here is, of course, potential due to a point charge. And we're going to take that equation. I'm having you guys start with these point charge equations, right? And then we're going to write that in a differential form. So when we write that in a differential form, that'll be dv equals k dq over r. The reason I'm doing that, you might say, why is she doing that? They don't do that in the book. I'm doing this because this is a really great skill that I want you to have. I want any student that's coming through my class to have this skill. And the skill is taking an expression that applies to a discrete something, right? In this case, it happens to be charge. But really, this skill can be extrapolated to a lot of different scenarios, which is why it's powerful. So taking an expression that applies to something discrete and being able to rewrite and then integrate that discrete expression so that it applies to something continuous. So I said that in a vague way, but that was on purpose. It's because this skill is a very transferable skill that you will use over and over again if you're going to be doing science in any kind of technical way that's going to involve math. So it will do you, it'll do you well. I still remember when I finally sort of got that this was a general skill and not a specific one. And that kind of unlocked for me being able to do a lot of different problems in physics. So I want to give that to my students, and that's what this is about. That's why I make you do it this way. Okay, so now I can go ahead and write out my integral here. So I know that the potential for the rod, or the potential at point P, right, due to the rod, is going to be me adding up or summing up all the dVs, and that's all the contributions of potential from every dq along the rod. So that's going to be that dV is, of course, k times dq over r. And now I'm going to substitute in my expression for dq and expression for r. And this is the same way we did it when we were finding E. I'm just walking through it again. If you got it the first time, awesome. Not everybody does. So k, and then I'll put in here lambda dx. That's my dq, right? Over r, and r in this case is a plus l minus x. The bounds of this integration, I look at my coordinate system and I have to look at x. X starts where and ends where for this charge distribution. The distribution starts at x equals 0 and it ends at x equals positive L for me, for my coordinate system. That could be different for you. So that's the bounds of my integration. So I could simplify this a tiny little bit here. I could pull out the k and the lambda, my constants there, and I end up with dx over a plus L minus x going from 0 to L. So I'm going to leave the integration and evaluation to you. You can look at those in the written solutions, remember that the integration and evaluation is certainly worth points. It's important, but it's because this isn't a math class, I don't spend a ton of time doing it in here. And when I teach face to face, I also don't spend a ton of time solving the integrals in class because at this point, right now, our physics is done. I still care about you being able to execute the problem, and I care about you being able to find your final result, and that's why you will see that all laid out in the written solutions, so be sure and do that. Okay, so our next step here would be to, integrate, and then we need to evaluate, of course. Okay, good, those are all skills that everybody, should have in this class. So the next version of this problem that I just wanna run through real quick is same rod, okay, uniformly charged, total charge, positive big Q, fine. But now I'm looking at this different point here. So I'm looking at a point R, that's above the end of the rod. So this is interesting. It's worth talking about. Um, just because it's a little different. You've looked at it in E-field stuff too, right? But now we're looking at it with respect to potential. So think about where you might want to put your origin. There are different choices that are good choices here. The choice that I'm going to make for this particular one is to put my origin now on the right-hand side of the rod. So right here is where my 0, 0 is going to be, and I'm going to put positive X leftward, positive Y upward. Okay, so hopefully that's clear. So positive J hat upward, positive I hat is leftward in this problem. So let's go ahead and go through it here. So same thing. I need to define my TQ. That's what this is so all about, right? That's always the starting block, is considering what is my differential element. If you don't truly understand your differential element, then you can't write the integral. You're not authentically writing the integral. You're sort of writing some stuff. But the integral should always reflect what that differential element is about. So yeah, that's my differential element right there, dq dx. And when you're doing your work on paper for the exam, if you want to use different colors, if that helps you, for some of us, it helps our brain to organize a little bit, and it helps our brain to kind of think really fast. So if that's you, use them. If it's not, don't. But I'll leave that up to you. Okay, so I will draw in my X. Then let's do the same moves we did for that last version. X, of course, is going to go from my origin to my differential element. So notice that whenever I draw these X's in, I don't draw an arrow on both sides. I draw it always coming from the origin, as it should, right? Pointing to my differential element. And then R is, as R always is, the distance between my differential element and the point of interest. So R in this case is going to be right here. And we're given that the rod length is L, and we're given that the distance between point R and the end of the rod there is A. Okay, so now let's do our defining stuff. So we know we need to define dq. We do this every time. This is not going to be a surprise. So dq, we're going to do again lambda dx. And we know we're going to have to shift out of lambda, right? So we know that we're going to have to do that. And that'll happen in both problems. We're given the overall charge and we're given L. So before we write our final expression, we need to rewrite it then in terms of Q and L. You should be comfortable at this point, especially with the one-dimensional charge distribution. So that's defining our dq. Now we're going to define R, as we have to do every time. So pause if you haven't done that yet and think about how you're going to define your R. And notice how the coordinate system choice influences the R definition, right? Like if you had you can think about redo this problem and put the origin on the left-hand side of the rod and notice that your R is going to look pretty different if you do that. So in this case, my r is going to just simply look like x squared plus a squared. So that was my motivation for using the right-hand side of the rod, as it really simplifies what that r looks like. All right, so I need to define my v. I'm using same equation, and I'm going to write that in differential form. K dq over r. And that's the form I'm going to use here. So I know that I'm going to define my potential. One thing I want to just mention real quick here that I didn't for the last one is that if you were solving for E field, the third question, remember when we were doing these things for E field, the structure that I showed you, it was define DQ, define R, and then we asked ourselves, is there any cancellation, right? You can still do that looking for symmetries and such. There is no cancellation in a case like this where I have only positive charge. It doesn't matter how symmetric or beautiful my situation is. This is not a vector. Electric potential is not a vector. So be careful when you are thinking about cancellation or symmetries or any of that thing, any of that stuff. It's a very, very different situation. Okay, that's all I'm going to say about that. So we generally don't do that step when we're looking at potential because we don't have those directional cancellations. So my potential for point R is going to be summing up all of my dVs, right? So I'm summing up K dq over R for my situation. And that's going to be K. My dq here is lambda dx. My R is root x squared plus a squared. So notice what a different form this is than the previous one that we looked at. So just kind of keeping an eye on that. And then bounds of integration here, I will be going from x equals 0 for, again, my coordinate system choice to x equal L. Our bounds always go from the lower to higher value. That's something you probably took away from a math class. And I can rewrite this to simplify it slightly here. Pull out the k and lambda, which are constants. And then I have dx over root x squared plus a squared going from 0 to L. Okay. So that, that's kind of what there is for that. After that, you would, of course, you'd integrate and then you'd evaluate to express your final potential. And that is, of course, what's all done in the written solutions. That's what you would need to do to finish the problem. Okay, well, I hope that this was helpful. It does have a simpler feeling to it than electric field by nature of it being scalar, but be sure still that you're keeping an eye on the quantity. It can be, I have had students submit work to me where they've expressed potential as a vector. That's not a great mistake to make because that shows me that you're not really understanding the quantity. And it's a harder, as I said before, I do think that it's kind of like a harder quantity to understand than E field in that way. Okay, that's all I got for this one. These two are really good problems for you to work through. Switch the coordinate system around. If these are feeling wobbly to you at all, switch the coordinate system around. Remember that you can go back to all of those electric field distribution problems that we did. Go back and solve those for potential. You can also do that.